So hello, and welcome to today's presentation on how to represent ball screws and linear rails in your analysis. My name is Paulo, and I'll be your presenter for today. And also on hand, we also have Jared Conway, who's the Analysis Services Manager, and Christopher Ma, who is the Lead Analysis Services Engineer. And all three of us, we work in the Analysis Services Department here at Hawk Ridge Systems, and we offer analysis consulting, mentoring, and custom training. So today, I'll be giving an overview of a consulting project that we recently worked on for Ingersoll Production Systems, who provides manufacturing solutions for their customers and is located in Rockford, Illinois. I'll be walking through the process we took for their analysis, mainly focusing on how we included linear rails and ball screws in a study that we created for them so that they could understand the performance of an automation machine that they were designing. I just want to let you guys know that we'll be recording this presentation so that if you guys wanted to view this at a later time, or if you guys run into any sort of meeting that you need to get to, you'll be able to access it through our website. Continue on here. So you'll also learn how spring connectors can be used to account for these types of assemblies in your own analysis. And we'll also take a look at the results we obtained and how the assumptions we made basically influenced the results. So before I go into the actual project that we did, I want to give you guys an outline of the analysis process we took and what's pretty much representative of what we teach during our mentoring and how we pretty much approach any type of study that we do for customers. So initially, we begin with having a meeting to go over what you're trying to achieve in a simulation study. And we also go over the application of the product you're designing and go over anything from the designs you currently have. We discuss what you're trying to understand about your designs. And from there, we discuss what we can do to get you the results that you want to use. So based on this information, we then put together a plan that includes the various elements that we discuss, and then we come up with an approach to obtain the answers that you're basically going to look for. And once the plan is in place, we then have an idea of what we'll do for the analysis, and we begin work on the project. And one of the first steps we almost always take, or that's involved in setting up a study, is simplifying the model that customers provide. So you can have a model that basically includes all the details, features, components that make up the real-life design, but including all these elements may not be the best approach when analyzing your designs using a simulation. And along these same lines, when we simplify the model, we also look into idealizing elements of your design, such as what I'll be discussing here, using spring connectors to represent the stiffness of your components. When making both model simplifications and idealizations, we also want to make sure that you understand the associated assumptions. And from there, next, we look at any input data we need or can be obtained. So this includes things like the material properties that you can give us or that's required that may not be included in SOLIDWORKS. And also, this may even include any kind of loading curves you may have to help define the study. From there, we try to see if we can apply this data directly or if we need to convert the data into something we can use in simulation. And once we obtain these results, once we have everything set up and put together, we then run the analysis in order to obtain results. And once we get these results. We then try to understand them to see if they make sense or if they're in line with what we expect, or at least what's in line, if they're in line with what our customer expects, and if they're reasonable based on the assumptions that we make. The final part of the analysis involves looking at any next steps we can take to basically understand more about the design that we created. So now, let's take a look at how we applied this process to include ball screws and linear rails for Ingersoll production systems. So Ingersoll basically wanted us, or was in the process of designing an automation machine, and one of their engineers actually posted a question on the SOLIDWORKS forums wondering how to go about setting up a study to account for the ball screws and linear rails that they had. And so they already had set up a study that treated these assemblies as perfectly bonded, and now they wanted to see how their design performed if they account for the stiffness data that they had for the ball screws and linear rails. And if any of you have actually visited the SOLIDWORKS forums or have looked at posts from the simulation section, you'd actually see Jared, or at least responses from Jared, who's helped others answer their questions, and he was actually the one who found this post on the SOLIDWORKS forums. So we actually contacted them to see if we could help them out with their study, and this actually led to discussions about the various aspects of their design that they wanted us to actually keep confidential for today's presentation, but essentially they were interested in understanding the displacements and stresses of their assembly under a worst-case loading condition, which they wanted to use to compare against results from that they would obtain from any design changes that they wanted to make. So after our discussions covering what they wanted out of the analysis, we then moved on to what we call here the planning phase. And during this phase, we try to answer any questions we have pertaining to a study that we want to create, and in order to set up a simulation that the customer wants to achieve their goals. So one of the first questions we try to answer is, well, what type of study are we going to use? And along with this is, what are the assumptions associated with the study type that we decide on? So in our discussions with the customer, we actually decided to go with a linear static stress analysis. And the assumptions that go with this include that all materials basically behave linear elastically. Materials are going to be considered as isotropic, and we're looking at small deflections that do not significantly affect the stiffness of the, or affect or change the stiffness of the structure, and all loads are basically going to be applied slowly, and the inertial effects won't be considered. So the next big question we asked ourselves was, what exactly are linear rails and ball screws? And to show you what we were given, I'm going to hop over to SOLIDWORKS here. At least show you the linear rail assembly. So we see a lot of designs, and we work with people from many different industries. And working with linear rails and ball screws was definitely something at least I didn't have too much experience with or familiarity with. And what we do here is essentially research to figure out different aspects of a customer's design. And for the linear rails, I found that essentially they provide free motion in one direction and are made up of a truck assembly, which are these two components here, and a rail component that essentially guides these trucks that actually contain ball bearings to allow smooth movement in a linear direction. So if I hide the rail, I can show you guys the ball bearing components that allow movement along the rails. And for the ball screws, so if I open up the ball screw assembly, essentially we have kind of the same thing. It's going to allow linear translation as this ball screw rod essentially rotates. There's bearings inside what's called the ball screw nut that act as threads that follow the helical pattern on the ball screw rod. And usually the rod is rotated or driven by some sort of motor that provides translation. And so if you guys take a look at the ball screw nut assembly, essentially there's going to be some ball bearings in there that again act as threads that ride along the threaded portion of the rod. So now, knowing what they are, brought up the question, how can these assemblies be included in analyzing the overall assembly? And in simulation, there's basically three ways we can include elements in an analysis. These include using the fully featured model, or simplifying the model for the analysis, or using a virtual idealization of the model. And so as I showed you in the pictures, or as I show you in the pictures here on this slide, and the example files, the linear rails and ball screw assemblies can include numerous features and components that can be time-consuming to include and set up in a study, especially when they're part of a larger assembly, as was the case for Ingersoll. So what we decided to do was actually combine the simplified geometry along with spring connectors in order to represent the stiffness that these assemblies would provide. And as we always kind of mention to customers during our mentoring, it's always good to start simple and from there progressively get more complex with your studies. So now, with a plan in place, we then start working with the files and work towards setting up a study. And as I mentioned before, we usually start by simplifying the models that we receive from customers. So sometimes we receive fully featured models that are ready to be manufactured. These types of files usually need to be simplified in order to save time and reduce the computational resources required to solve a complex problem. So the question that comes up is whether to use the original files or make a separate model specifically for simulation. So what we did for the ball screws and linear rails was utilize configurations in order to separate the fully featured detail model that the customer provided from the one that we will actually use in a study. And I actually encourage you to do the same when working with your own parts and assemblies, because it allows you to switch back and forth more easily between what you would create in real life versus what you would use in a simulation. And basically, to take things further, it's good to create simplified configurations at each level. And to show you, let me again switch back over to SOLIDWORKS here. So if I go back to the linear rail, you'll see that the truck component basically has a fully detailed model, so it includes things like the bearings, all the holes that would be threaded. It may even contain, different parts that, or bodies that may be different material, so on and so forth. But what I recommend, or what I'm describing here, is to actually create a configuration that will be used specifically for the analysis. And what we did was basically remove all the complex geometry in order to simplify the model and to help us define inputs for the spring connectors that we'll use in the actual simulation study. And to do so, we actually also created split lines. So these different faces were separated in order to help us create selections for the inputs to define the spring connectors. And from there, what then we do, so you can do it at the part level, right, with the fully featured and then a for analysis configuration. But if we go back to the assembly, you can then take it further by having the same fully featured assembly, which references the fully featured part configuration, and also include a configuration where you reference the configurations that are for analysis. So again, this is where having that tiered structure can be beneficial for you in setting up a study, as well as in providing a representation for manufacturing. So as I mentioned in the planning portion of the study, we then decided to use spring connectors along with the simplified geometry in order to account for the stiffness of the linear rails and ball screws. And this would provide us with a good balance between essentially accuracy in our results and solve time. So what Ingersoll provided us with were data sheets from the manufacturer for these assemblies, which we would then use to define the stiffness for the spring connectors that we wanted to include as well. And you can see in the slide here that we have 3 different data sheets representative of the different loading directions that the trucks or the linear rails gave with regards to deformation versus the load being applied. And then for the ball screws, we were given just actually a single rigidity value, and I'll describe how we used all these in a moment here. But basically, during our research in understanding what ball screws and linear rails were, we also looked into how these assemblies were tested and where the stiffness data came from, essentially, in order to understand how the assumptions we make based on the plan we set out to use spring connectors could affect the results. And it was found that the stiffness and deflection curves that these data sheets provided were representative of the entire ball screw and linear rail assembly. So our assumptions to include the simplified geometry and spring connectors would actually be assuming a stiffer model than what's provided here in the data sheets. And this is because we're also including the geometry that accounted for that makes up this stiffness data in our study. So how we interpreted the data to use as inputs for defining the spring connectors, and which I'll actually be describing in the next slide, there was a compromise in the stiffness that we came up with, that in the end provided reasonable results that we could use to compare with results for any design changes that they wanted to make. So now we needed to prepare the data now for simulation in order to again create usable inputs to define our spring connectors. So Ingersoll provided again these data sheets, and the linear rail data showed basically the deformation as a function of the load being applied, and that data essentially needed to be turned into a stiffness input for defining the spring connectors. And as I'll show you in the setup of in the analysis, but what I'll mention just for now, when defining spring connectors in SOLIDWORKS simulation, you define the stiffness in a normal direction and a tangential direction as either a distributed stiffness across an area or a total stiffness. And the linear rail data that we obtained needed to be converted to values that we can use as inputs for the spring connectors. So what we decided on was to obtain slopes from one of the curves for each of these three loading conditions which were provided, which will then be representative of the stiffness in that particular direction for the linear rails. So you may be asking yourself, how can an accurate slope be obtained based on what we're given? So there's actually a neat little application here that I'll open up. It's called the Plot Digitizer tool. And this essentially allows you to convert graphs, which we again have as the data for the balls, or the linear rails rather. And what you can do using the Plot Digitizer is actually import or open these graphs, as long as they're actually saved as a picture file. In this case, it was a PNG. So when we open it up, we can then use this to create data points that we can then bring into Excel to create essentially a plot, to create obviously a trend line, and from there we can then obtain a slope of these plots. So to do this, you essentially follow the instructions here on the bottom. See if you guys can see this. So it says choose the most negative end of the x-axis. So in this case it'll be the 0 component. And we'll input 0 as the most negative. And we'll also input 0 for the y value. Then it says choose the most positive end of the x-axis, which we'll choose here. And that value is going to be 55. And then also the most positive value along the y, which is also 55. And then we can give it a name. I'll say the x-axis is load. The y-axis is deformation. And with the axes defined, or the axes defined, we can then start digitizing our plot here, essentially creating points that we can use in Excel. So one thing to mention, we chose to go with the V2 curve, basically in our discussions with the customer as far as which curve to use to define, or that they are using for their linear rails. It was decided that the V2 curve is representative of the stiffness for the ones that they were using. So essentially we can start picking points, and obviously the more points that you pick, as well as how close you are to following the actual curve will allow you to get a more accurate representation of the plot that you're trying to get data points from. So I'll just click a few points here. And then once you're done, you can then go into this option here, click Done, and from there you get points that you can then basically use and copy into Excel. So I actually have the Excel plot, so I'm just going to close out of this. So again, what we do is take those points, copy them into Excel, and then we basically can create the same curves that's in those data sheets. And from there, what we did was essentially create a trend line of those plots, assuming, again, these were somewhat linear, and from there we took the slope, which is then the amount of deformation per the load applied, and then transform that into the load divided by the amount of deformation, basically taking the inverse. So again, based on discussions with the customer, the lateral stiffness, this one here, is essentially would be used for springs that connected the two side faces of the rail to the truck, and I'll show this in the actual setup of the analysis. And then an average of the compressive and tensile stiffness data was used for springs that connected the top face of the rail to the truck. For the ball screws, so again, we were given just a single rigidity value. And again, in SOLIDWORKS, we have to convert that rigidity value due to the inputs that I'll show in the setup. We had to make that per unit area, and what SOLIDWORKS simulation uses is actually the average area between the faces that you select to define the spring connector. And so this rigidity value was then divided by that average area, and that gives us then the input that we would use for defining the spring connectors for the ball screws. So now, let's go into the setup. So as I mentioned, basically once we have everything prepared and we have a plan now, it comes now time to set up the analysis. And bear in mind that I'll be showing the model in just a second here, but we didn't include the full assembly, which would have a frame structure that the rails and ball screws would actually be mounted to. But give me a second here and I'll switch over to SOLIDWORKS to show you what I mean. Let's close out of these. And so here's kind of a example file that I created to kind of describe what the setup was for the actual project we worked on for Ingersoll. And if I go to the simulation tab here in the bottom, basically the material that we chose was going to be the default 1023 carbon steel sheet from the default material library. And this was so that Ingersoll could use it or make this study comparable between, again, the previous analysis where they ran the the assembly as fully bonded. Next comes the connections. So I'll get back to the spring connectors in a moment, but we treated basically every other component that's initially touching as perfectly bonded together. And then from there, we defined fixtures. Again, I didn't include the frame, but for this example, I fixed essentially where the linear rails and ball screw rods would be mounted to onto the actual frame. We also applied the loads that we discussed during our initial phone conversation. So they wanted to look at loading in a couple directions. And this again is loading, at least what they considered as the worst case loading scenario. In the actual analysis that we also ran, we included gravity to account for the weight of the actual components being used. In this example, I didn't include that, just for another topic I'll be discussing here in a moment. Basically, going back now to the spring connectors, discussions with the customer essentially led to the decision that the axial directional stiffness was only going to be really accounted for in the ball screws as opposed to also in the linear rails. So let me just edit the definition of one of the truck components for the linear rails here. Essentially, we didn't want, or they didn't want to provide a stiffness in the direction that the trucks would slide along the rails. And that made sense, right? Because there's ball bearings, and that would allow essentially free movement along the rails, whereas the ball screws rather are what provide that rigidity due to the ball screw or the bearings that act as threads that travel along the threaded rod. And so, depending on the orientation of the truck, we chose to define just the normal stiffness, but the value that we used was either going to be, again, the the lateral loading for these two faces, this one as well as the opposing face here that connected the linear rail to the trucks. And then we used the average tensile and compressive stiffness that we got on just the faces that connected the top of the rail to the underside face of the truck. And also, from there, defining now the ball screws, what we did was choose two concentric cylindrical faces, since again we simplified the model basically down to a cylindrical rod and then a circular hole. And to account for the stiffness in the axial direction, we used or decided to use the rigidity value for both the radial direction as well as the shear direction, which would then give us that axial stiffness that we're looking for that only the ball screw would provide. And so with the analysis set up, we then move on to running the study. And from there, we then obtain results. And in this case, again, where Ingersoll was really only concerned about the displacements and stresses. And going back here, so I'll show you in a minute here back in SOLIDWORKS, but Ingersoll wanted the plots to be consistent with what they did for their fully bonded analysis, where they made essentially the maximum and minimum values in the plot legends the same across the X, Y, and Z displacement plots. And again, this just allowed them to compare the plots more easily. They also wanted the minimum values to be the inverse of the maximum. So it might sound a little confusing, but I'll just go back into SOLIDWORKS and show you what I mean. So if we look at the results for the displacement, at least the X displacement, I only plotted one component. But here's the default plot that we obtained from SOLIDWORKS. And as you can see, it's just this is the default color scheme, and it's whatever the minimum is and whatever the maximum is for that particular plot. And what Ingersoll wanted, and what you could do is essentially adjust the plot to have the maximum, or the minimum rather, be the inverse of the maximum. Again, this is just to compare results between their previous analysis, but I just thought it'd be worth mentioning here to show you at least something you can do as well. So what we recommend when creating plots like this, especially when you create an adjusted plot that's different from the default plot that's provided, you actually want to, when outputting results, is show that default plot so that the reader or the people that look at your results understand where that adjusted plot came from, or how you may have created the adjusted plot scale. And a few tips when reporting your results. And what we do is actually change the background to white. So let's say, again, you're going to make a report out of the results you get from a study. You can then go into your background here and change the background to plain white. And what we do to create screenshots, as opposed to using the default reporting option where SOLIDWORKS will automatically create screenshots for you, is use a tool rather called Jing. And if I bring that up here in just a second, you can essentially create a screenshot that you're looking for, give it a name, and as well as mark it up. So if you wanted to, indicate, hey, this is an area of concern, you can create boxes and input text. That will allow you to indicate to your readers or people viewing your results, essentially the results you're trying to get. And another tool that's even free within Windows is called the snipping tool. You don't get quite the control you do with Jing, and that's why I prefer Jing over the snipping tool, but it's essentially the same thing. We do recommend making really your own screenshots because you can orient the part the way you want, as well as get the sizing right and really show off what you're trying to convey to whoever might look at your results. From there, the next step in our process, again, is to now understand the results that we get, right? Because may not be sure that the results we obtain are really representative of what's going on. And just to point out, here's a link, or here's the link to download Jing if that's something you're interested in. So validating results, once they're obtained, one of the first things you want to look for is the reaction forces. It's definitely something that's simple and easily obtained from within SOLIDWORKS. You just want to make sure that that the amount of load that you're putting in equals the total load or total reaction force that's being handled by the fixtures. And to do that, let's go in here, and you can right-click on the results and choose the option Resultant Force. And choosing the reaction force option then allows you to select faces that you define for the fixture. And clicking Update on the model, we can see here that the amount of load, again, was going to be that 1,500 pound force input in both the X and Y directions is equal to the total reaction force that's going through the fixtures, essentially making this the static analysis that we set up. The next thing we wanted to look at, or another check that we did to ensure that our results are okay, is to actually look at components that may be interfering with each other when they're displaced. So hide these. What you actually want to do is actually look at the true scale. So true scale is essentially representative of the actual deformation that's occurring. You wouldn't want to see too much, but being a static study, but looking at, or what we were concerned about, was whether the ball screw rod might be interfering with the frame structure here. And as you can see in the true deformation scale, we're not seeing any interference between the hole that the ball screw rod goes through. If there was, we would need to define no penetration contacts, or we may have needed to look into whether the stiffness of the ball screw spring connectors were defined properly. And same goes for, again, the definition of the linear rails. We wouldn't want to see excessive displacements where maybe, the frame or this structure here or component was flying off or derailing itself from the linear rail. And again, what the customer provided was a fully bonded analysis. And as another check we did was to compare our results against a fully bonded scenario. And the check was essentially the fully bonded scenario should be stiffer than the analysis where we're using spring connectors. And looking at the displacements, we got, or at least in this case, we got a 3.8 or actually 38 micron displacement in our study here. And if we go to the one that contained the spring connectors, you should expect the same behavior, but actually it's going to be more displacement than the fully bonded, which we would expect to be more rigid. And to further check our setup, we also wanted to look at the exaggerated displacement, where we would actually expect the results or the shape to be similar between the two studies. Not necessarily exactly the same, but we want to make sure that we're getting the same behavior in order to see if we may have missed a definition in the spring connector, or possibly another aspect of the analysis was overlooked. And looking at the bonded case here, again, we're getting kind of the same expected inward deflection or deformation. So once we have the results and we presented this to the customer, we then go into a discussion about actually one last thing. The next thing, once you set up a study and get everything validated, you're getting expected results, you know what you want, you then start looking into whether the mesh you have, and with that, the numerical accuracy of your results is valid. And to do that, what we did was, again, look into a finer mesh in order to see the trends in the results and whether what we were getting was believable. So I'm not going to show the actual results, but I'll describe what we did to obtain a mesh, an appropriate mesh for this analysis. So again, we had a larger assembly than what I'm showing here, but the main concern we wanted, or what we wanted to achieve with the mesh, was 2 elements across the thickness in the areas of influence. And what we were finding was that the areas of influence were essentially the ball screws and linear rail components. And if I show the mesh here, so this is the more refined mesh. This might take a second to load. But again, applying a mesh control can allow you to get the appropriate mesh that you're looking for. This actually looks to be a little more refined than what we set out to do, but again, applying mesh control, allowing you to select the appropriate bodies and or faces will allow you to achieve a mesh that will provide the accuracy that you're looking for in your results. So now, again, once we validated our results, we now go back and discuss with the customer the next steps that they can take. And there's kind of 3 approaches that customers usually take when looking at what they can do to further understand their designs. And working with Ingersoll, they wanted to actually look at a design change based on the results that they were getting off of the initial analysis that we ran for them. So what that allowed us to do is essentially apply the same procedure to the analysis, to the new analysis on the new design, in order to obtain results showing whether the change they made improved the performance or not. And since we had an analysis that we could use for comparison, and we validated the results and know that it's working properly, we essentially applied the same setup and made the same assumptions to the new design that helped them choose between either the new design or the design that they had previously. Another topic of discussion that can come up is even changing the loading condition. And in Ingersoll's case, they actually wanted to see if one design was better at handling a particular load direction versus another. And so we actually ran a couple more studies to see if one loading direction influenced the design of their assembly more than the other loading condition. And another approach that customers can take is correlating the results to physical testing. We didn't do that with Ingersoll, but definitely once you do have a final design, reducing the number of assumptions in your study and spending the time to correlate the results for physical testing could be beneficial. And in the case for Ingersoll, one thing we could have done is definitely correlate the stiffness we used in the spring connectors to the physical testing or a physical test of the actual linear rail or ball screw assemblies, so that we can adjust those stiffnesses, essentially providing more realistic results where we're not, in a way, doubling up on the stiffness by including the components that made up those linear rails and ball screws. So in review, hopefully I gave you guys an idea of the approach that we take for studies that we do, as well as the process that we teach in our mentoring program. More specifically, how this approach was used to set up a study that involved linear rails and ball screws. And hopefully you understand that we use spring connectors in our studies to account for ball screws and linear rails. But if you guys have any other methods for approaching an analysis like this, definitely feel free to comment. Also, if you have any questions pertaining to what I presented today, please feel free to post your questions in the control panel there, and either myself or my colleagues can help you out or answer your questions. And I'll give you guys a second to post anything that you have questions about or you have any comments. And again, just feel free to leave your questions or comments. And I just want to let you guys know about our upcoming Webinar Wednesday schedule, where you can either learn how to use the software through our e-learning series, or see a live demonstration of other solutions that we offer in our e-demos. And one last thing I want to mention here is that we're giving a 10% discount towards all who participated in today's webinar. And again, this is going to be a 10% discount towards any analysis consulting, mentoring, or custom training that we can do for you. And with that, or if you want to contact us, again, here's our contact information, and you can get to us either by email or phone. And I just want to thank you all for taking time out of your busy schedules to attend today's presentation, and have a great rest of your day.